By popular request, I want to introduce you to MPI for Python. This is a pretty cool wrapper around the MPI libraries. So under the hood, it's still the same kind of things we've been running from C, but Python's been wrapped around it, which makes it kind of more fun and probably a little easier to use. So this is the main documentation page for MPI for Python. It's called MPI for Py at readthedocs.io. Some of the things that you might want to take a look at in here, certainly this little introduction kind of gives you a little idea about why they did this, what's MPI, how does Python connect, some other things that you might be interested in reading or knowing about. There is a really nice tutorial here that walks you through how to do most of the things that you're familiar with. Well, certainly all the things you're familiar with from the C interface and a bunch of other stuff. There isn't super great kind of reference API documentation for the whole thing, but all the examples of things that you're going to want to be able to do are in this file or in this website. So, for example, here's a very simple point-to-point communication thing where we're using, again, the com world communicator. We're calling a function on that gets our current rank. We can compare that with 0 or whatever the rank number we're interested in. When we want to communicate, it's really easy. You can just use that communicator and say send, and then the data you want to send, and then the destination processor and the tag. And I think you can even leave the tag off if you don't care for what the tag value is. And you'll notice here that we're just actually sending a value that looks a lot like a Python data structure, which is exactly what's going on here. So we create this as a Python dictionary. We send it across using MPI. The MPI for Py library takes care of all the encoding and decoding. And here on processor 1, we can just do com receive from process 0, and in this case, supply the equivalent tag. And this data will now be exactly the same value as the sent data, but on processor 1. So it couldn't be simpler to send information back and forth. It's probably not super efficient because MPI for Py has got to do some sort of encoding of this structure. It's like using the standard pickle module or something like that. So it's not super efficient, but it's certainly serves to give a sense for how to use the MPI library and how to architect your algorithms in Python. There are faster ways to do this. So for example, if you've done any kind of numerical processing in Python, the NumPy package is super popular, and it provides basically a C language implementation of arrays for Python to use. So they run at essentially C speed, and you can also use NumPy objects in your MPI for Py programs. There's some other information here that you might want to take a look at to just look at some of the different things that we've talked about already and that you might want to figure out how to do in Python. If you would really like to drill into more of the details, the good news is, of course, that this thing is open sourced. So up on GitHub at MPI for Py, you can find all the source code for this. Couple of useful places to look here are in the test directory. So there's some really nice, thorough PyTest type tests in here that you can take a look at to see how you actually call these things. So like test communicator.py here, you can see how they're testing different communicators, every way till Thursday. So if you get stuck figuring out how to call some function because the documentation might be a little lacking, you probably can find a test that works with it. Or you can also just look at the source. So inside the source code, in the MPI for Py directory, you'll find under MPI all of the implementations of these objects. This is actually a Python kind of a file, so it's kind of a mixture of Python and C in a way. So for example, let's just look at message. I'm just picking something at random. You can see here it's a class that's being defined for Python, but it's implemented largely in this C environment that uses the actual MPI libraries under the hood. So I'm not going to really go into the details of how to use Python, but this would be another place where you could go to look for the details. So you can kind of dope out the arguments that are expected to be passed and what they do and whether they have defaults and stuff by looking at the source code. Okay, so let's take a look at some code here. So what I've put together, and I'll make this available to you, is a handout file that's got some starter code in it. And let me open up a shell here. And I'm going to unpack that tarball. So tar extract verbose zipped file handout.tar.gz, and then I get this handout directory. All right, so what's here? First of all, this is Python, obviously. And when we're working with Python, we want to usually set up a virtual environment that has all of the details for our particular Python project, rather than trying to overwrite the default installation of Python with other libraries that maybe we're only using on one project. It's very common to set up a virtual environment. And under Python 3, that's super easy to do because the venv, or the virtual env environment module, comes with Python. I'm using Python 3.8 point something here. Let me get the actual version number. Python 3 version 3.8.6. And I am using some of the newer features in Python, like the Walrus assignment operator. So if you have a version of Python that's less than 3.8, you might run into some problems. So what we want to do is create a virtual environment. So we'll say Python 3, and then the module you use, which you can get to from -m, is called virtual, or venv. And I usually just create a virtual environment called venv. You can call it whatever you want, but I'll just kind of use my usual convention. And then that's going to cook for a second. And what we'll see here in our directory is that we have a new directory called venv. And if we, let me go back up here. If we drill down inside of this, it looks kind of like a standard Unix file system, right? There's a bin and an include and a lib. And what's going to happen here is, as we install modules that we want to use in this project, it's going to install them in this directory, not in our default system-wide Python. And then in order to make use of this virtual environment, we need to use this script here that's called activate. And you can see that there's some other binary things in here. So Python 3 and Python are both in here, the pip program for installing packages and whatnot. But what we want to do is tell our shell that this is the virtual environment that we want to use. And that's the job of that activate script. And you can't just run it. You have to source it into your current shell. So back down here in my shell, I'm going to say source. And then I'm going to go to venv bin activate. Again, you don't want to just run this. You want to actually source it into your shell so it changes the configuration of your shell. And one of the things it's going to do, for example, is update your path so that you're pointing to the executables that are in the virtual environment that you just installed. Okay, and the default behavior, it gives you this little venv thing here showing up. I think that's kind of ugly looking, so I've integrated that into my little fancy shell prompt here. So I'm going to just say, make my main shell prompt equal to the result of running this fancy prompt program. And now it just kind of drops it into my command line thing, which I like a lot better. Okay, so now if I say which Python, you can see here that I'm getting the Python I'm just running in my little temp directory here in that handout. And there's the virtual environment and the bin and then the Python. So that Python there is this Python here. So we are now running the Python that's there inside the virtual environment. And that means that if we install packages like MPI for Pi, they're going to go directly into this virtual environment and not get in the way of any other installations of Python that we might have on our system. So I'm going to go ahead and install some modules. Now, another convention in Python, if you're not familiar with it, is that a file called requirements.txt is often used as a kind of a manifest. It's kind of like the Python equivalent of package.json in the Node ecosystem, for example, where it basically lists the modules that need to be installed in order for this code to work. And what it does is basically just gives the name of the module and then the version number that you're after. To install that, you can use the pip command. And again, like with Python itself, the pip command is the one that's coming out of the virtual environment. So if we say which pip, it'll tell us it's the virtual environment one. So I sometimes just like to check to make sure that I'm getting things from the virtual environment so that I don't get caught up running the wrong thing, because there's probably also a pip installed with the operating system. So we're going to run pip, and the install command is what we use to install modules in pip. And to specify a particular requirements file, you say -r and then requirements.txt. Again, that notion of requirements.txt is not required. It's just kind of a convention that is observed pretty consistently across the Python community. So if you download a new package and you want to work with it or contribute to something out there, and you see that requirements.txt file, it's a good hint that that's the thing you should probably install to get started with that package. So you can see it also does dependency management. So although there were only 2 packages listed in my requirements.txt file, it installed a bunch of other ones as well. And there'll get a little warning here about pip being a little out of date, which we don't really care about. So what's happened now, if we go back up here and refresh this directory, is that in our lib, we've got a bunch of packages that are installed just locally inside this virtual environment. So all these things, including, you can see MPI for Pi here, all those things are now installed in our virtual environment. And as long as we remember to source that bin/activate script into our shell, we can just use ordinary Python commands, and we'll be getting all of our runtime stuff from this library. Okay, so that's basically how to get started. Now let's take a look back up at our source files. So let's see where to start. Let's look at this matrix class here. A couple 3 classes in here. Hopefully this isn't a complete review for everybody, but I wanted to show you maybe some Python programming techniques you might not have seen before or might not have seen recently. But the first thing is Python obviously is an object-oriented language. If you're not thinking in terms of classes and class hierarchy and how classes interact, you're probably doing it wrong. So I'm using a set of classes in here, and the top level one is a class called matrix, and here's the Python constructor, and I'm basically have 3 instance variables here: the number of rows, the number of columns, and then data is just going to be a 2-dimensional array of integers basically. So this is my constructor, and you can use this to pass in a number of rows, number of columns, and then a nested array of whatever values you want to store there. So that's kind of the lowest common denominator constructor. You can also define in a Python class more sophisticated constructors that ultimately use that underlying underbar init thing, but they might do some more stuff. So I've got several different ways to make a matrix object here in this implementation. So first of all, there's a from data. So the idea here is you could just define a doubly nested list of lists containing integers and just hand that to this function, and it will create a matrix object that's populated with those data. So what I'm doing in here is just a very simple approach to filling out the rest of the details for this matrix. So I've got that array of arrays of integers, and I'm going to ask for the length of that top level array, and that's going to correspond to the number of rows in the matrix. And then I'm going to ask the length of the first element inside that array, which itself should be an array of integers. And I'm just assuming that whoever is calling this method had the wherewithal to make sure that all the rows were the same width. So it might go haywire if that's not the case, and you could add some error checking here to make it more robust, but this seems plenty. So that gives us a number of columns. Now what I want to do, so far I haven't actually created a matrix object. I've just started this function. I've designated this though as a class method. So this decorator may be something you've seen before, maybe not, but it basically just says, hey, this is not a method that's defined on an instance of a matrix. It's defined on the matrix class itself. So just like you can call the class with a function call syntax to invoke the constructor, the dunderbar init function. In this case, if we want to be able to create a matrix from the data that we pass it, we can call the from data method on that matrix class itself. And because this is designated as a class method, we don't get the instance of something, which is what we normally get in a method. So normally that's called self in Python, although it doesn't have to be. Instead, it's common to have the first argument here be called CLS, or some people spell class with a K, which I think is kind of darky. But CLS basically means we're getting the class itself as our first argument. And what that allows us to do is call class methods on the class, which is exactly what we want to do here when we're constructing a new matrix. So you can see here I'm actually calling the class. So that's the equivalent of invoking the matrix as a function, right, which is how you call a constructor in Python, and I'm passing it the rows and the columns and the data that I received. So the caller sent me the data, and I figured out the rows and the columns so that I could turn around and call the matrix constructor as this class is that matrix itself. So that's going to call this function and store in instance variables rows, columns, and the data, right? So you can call that function manually, but I figured there was some other kind of common use cases that might be handy for this matrix class. So that's the data constructor. Here's another constructor that gives you a new matrix that's empty, and it has a particular size. So a certain number of rows and a certain number of columns. And again, we get the class itself so that we can call the constructor. And what I'm going to do here is create a matrix of matrices, or excuse me, an array of arrays. And what I decided to put in here is, rather than assume that this was always going to be integers or whatever, I just decided to create an array of arrays of the value none, right? That's kind of the null value in Python. So I'm using list comprehensions, and if you are unfamiliar with list comprehensions, I'm not going to go into them in detail here, but I would really encourage you to just Google for some articles about how they work and how to use them. They're super helpful for processing lists as well as dictionaries. So essentially what's going on here is I'm creating an array here that contains a value none for as many values as there are in this list, or in this value of columns. So this is going to create an array of nones that's as long as the calls value. And that's going to be wrapped up inside a second list comprehension that's going to create one of those sublists for every list in the outer invocation here, which is going to be as many values as there are rows that I passed in. So that's going to construct an array of arrays where there's rows, inner arrays, and each of those arrays has calls number of nones. And then as I did before, all that I've done so far is created the data, but I have to actually use that to instantiate a new instance of the matrix object or matrix class. So I call the constructor again and pass in the rows and the columns and the data. It also turns out to be handy to create arrays that contain random stuff, right? That's a lot of what we use for kind of test data for our development. So I've got another constructor here called fromRandom, and it takes a number of rows and a number of columns, similar to the from size that we just looked at. And I've also passed in a couple of optional parameters here called min and max, so you can set the range of values that are going to be generated into that random array. So I've given some default values. So by default, this will generate an array of arrays that's rows, columns, or rows tall and columns wide. And the elements that are going to be stored there are going to be random integers in the range from 1 to 100. So I'm using, again, a list comprehension here, but instead of just pasting in none for all the values to just give some placeholders, I'm calling this standard library function randint. You can see at the top of the page here that I'm importing that from the standard random library that comes with Python. And everything else is pretty much the same as the from size function. So I'm just generating random integers, and notice that I'm using min and max as the range of values from the parameters here. And then I call the constructor to actually generate the matrix object. So we have these different ways of constructing a matrix. Some other things I've got in here, you're familiar hopefully with the constructor syntax with the dunderbar init function. And you probably have also seen the underbar to underbar string function. This takes the internal structure of the object and converts it into a string format. So if you have a matrix instance, a matrix object, and you hand it to print, the standard Python print function, that it's going to have to convert it from its internal representation into a string. And the way that Python knows to do that is to check to see if there's an implementation of dunderbar string, or str, which is what we're showing here. And notice that this is an instance method. It's going to be called on a specific array, not to construct a new one. And again, I'm making use of some list comprehensions here to construct a reasonable representation of what that array is going to look like. So I'm going to put the size of the array in the output. And again, I can just reference self.rows and self.columns, which got stored up here when we eventually called the constructor, whether directly or from one of these other constructor functions. And then I just create a list of lists containing the values in the array. I'm using stir to cast them into strings, and then joining them together with spaces. So it couldn't be simpler. And then at the end, this generates all of the lines in this return variable, and then at the end I join those all together with new lines between and return that string, and then print in turn sends that to standard output or whatever file descriptor we pass to it. This is really about matrix addition. And so I thought, because we have this object, this Python object that stores a matrix, we should use the Python capability to overload some of the actual operators in the language. And if we define a function called dunderbar add, it's a method that will be called when we use the plus symbol in our code. So the way that this works is we get the self is going to get a matrix on which we called the plus, or invoke the plus, and other is going to get the second matrix that we're going to add to the first matrix. So self and other are both instances of the matrix class. And I'm doing a little bit of checking here. So for example, we know that we can't add two matrices together unless they have exactly the same number of rows and columns. So I'm verifying that that's the case, just for yucks, and then raising a runtime error if that doesn't happen. Then I want to do the addition, and of course there's no substitute other than just kind of doing the doubly nested for thing, as I've shown here, to walk across each of the rows, or walk down all the rows, and within each one walk across the columns and do the addition. Now I have to have someplace to put the sum, so I'm using, as you won't be surprised to find, this from size function, right, that we talked about up here. So what's going to happen here, and notice again that I'm invoking this as a class method. I'm calling it on the matrix class itself, not on an instance of the matrix. So matrix from size, and I'm passing in self.rows and self.columns. So I could have arbitrarily chosen to use other, since I've already verified that the rows and columns in both of those input matrices are the same. But that's going to create a matrix that has that many rows and columns, and the values in those inner matrices are just going to be the value none. And then I'm going to, and I hold on to that matrix as matsum, and now I'm just going to iterate over the number of rows and the number of columns, just using the standard range operator, which is going to give me an iterator that goes from 0 to r-1 or from 0 to c-1. And then exactly what you'd expect. The data themselves are stored in the data instance variable inside the matrix. So I'm going to set the value of matrix sum of that location to the value of self at that location plus other at that location. So I'm kind of reaching inside the matrices, pulling out specific values, adding them together, and putting them in the returned matrix. And then what this guy does is returns matsum. And let me just quickly go to an example of how this is used. So here, I'm going to come back and talk about this matrix reader here, but this is basically reading in the A matrix from a file, the B matrix from a file, and then I'm just calling add, right? So this is going to be a matrix instance, this is going to be a matrix instance, and calling A plus B under the hood is going to invoke that dunderbar add function, which is going to give us back another matrix that I'm going to store in C. So again, we can overload those standard operators like plus, and most of the rest of them as well, in this fashion. So let's go back to that matrix file. Now, initially, I had tried to sort of shoehorn the I/O stuff into the matrix class itself, and I just decided that that was kind of clunky here after a while, and I decided to separate it out. So I've got two new classes here, two additional classes that are responsible for reading a matrix from disk and writing a matrix to disk. I guess I could have combined those into one, but I chose to split them up. So if you think about the process of reading and writing these matrices, first of all, one of the decisions I made is to have the matrices be self-describing. So they aren't just files full of numbers that represent the data. they actually start with the number of rows and the number of columns, and then all the data for that many cells. So when we open up one of these files to read it in, the first thing we've got to do is peel off the first line, basically, that has the size of the matrix. So I'm reading that in right away from the file and storing it in two instance variables called total rows and total columns. So the reader is aware of the overall size of the matrix, and that is important in some cases when we're trying to read the entire matrix, or if we're trying to read individual sort of stripes of the matrix, a group of rows at a time. That's helpful as well. So again, I'm using a list comprehension here. It's going to take the line, and using the split operator, which just separates it at white space, that splits it into two strings containing those integer values of the number of rows and columns. And then I'm passing that to the casting operator int to force the integer values from those strings, and then capturing those two values in this in the left-hand side of the assignment statement. So at the end of the constructor, I have the file pointer that's open to the file, because I might want to read multiple times from the same file. And I also know how many total rows and total columns are in the matrix in that file, should I need that information. I've also defined a destructor. So the del operator is run when the garbage collector deletes an instance of an object. So just in case I forgot to call close on that file pointer, I've done it here. Actually, that's an error. It should say fp.close. And then I also have defined a close function itself. So, if you're writing well-behaved code, it should open the file or open the reader, read the contents of the matrix, and then close the reader or close the underlying file. So close checks to see is the file pointer already closed. If it isn't, then it calls close and indicates that it has been closed. Okay, the interesting parts of the reader then are these two pieces. So after we've opened the file and read in the size, now all we have left at the file pointer is a series of rows. So the way I store the data is one row of the matrix goes in one line of the file, and that line just contains as many column values as necessary, separated by spaces. So what read rows does is it just reads the next number of rows from the file. You can pass in a parameter here. Again, here's just some kind of Python programming techniques. If you give a number here, if I say 10, this function is going to read the next 10 rows. And if I have 1,000 rows in the file, I could call that 100 times to read 10 rows. And if you don't specify the number of rows, then I give it a default value so I can tell that you didn't give me a value. And in that case, I'm just going to read the file until I run out of rows. So it's going to finish reading the file, or maybe I haven't read anything so far other than the size, in which case it'll read the whole thing. So I've got an array that is going to contain the rows that are being read. I'm counting that. I could just use, I don't want to call length on this a bunch of times, so I'm keeping a parallel counter. Here's the Walrus assignment operator that allows us to use an assignment inside of a looping construct. And again, you need Python 3.8 to use that. So this works a lot like the similar construct works in C, where you can have a while loop that iterates over something, and the contents of the control structure for that while loop can both be an assignment and also be used as the value to be compared to determine whether the loop is over. So I'm reading in a line from the file pointer, calling just the standard Python read line function, and then keeping track of the number of lines. And then again, I'm using a list comprehension for this with the same kind of strategy as before. I'm reading in a line that's got a bunch of integers that are separated by white space. So I use line.split to take that string that I read in and split it into an array of strings, and then coerce those individual values into being integers, and I store that in a row. And then I call rows.append of row. So this is just going to stack up a list of rows as arrays of integers inside of this top level array, which is the thing I'm going to return back to my caller. And then I got to do some logic here to check to see if it's time to stop reading. So if numRows is not none, this is the right way of checking against none. You shouldn't ever use equality or the double equals to compare for none, because none is actually a separate thing. If the numRows is not none, in other words, I sent a value in for numRows, and the number of rows that I've read is is equal to the number of rows. I guess I'm being a little paranoid here. I should hit the equality comparison, but just in case something weird goes on, I'm also checking for greater than. If that's the case, then I just do a break, and that will break out of this top level while loop and drop me to the end. On the other hand, if I didn't give a value for num rows, then this will be false because num rows will be none, and I'll just keep reading rows until I run out of them, which will be detected by this while loop, because when read line is out of lines to read, it returns a falsy value. So, and then eventually I'm going to return those rows back to my caller. So I can read any number of rows kind of from the current file pointer that I'd like to. And then it also turns out to be convenient to just go ahead and read the entire file into a matrix. So I've got a second function here called read matrix. Also takes a number of rows in case I want to take and instead of returning a list of rows, I want to return a matrix containing those rows. I can stop down the number of rows that I read, and so that basically just uses this read rows function again, right? I'm going to call that and read that many rows, and if I don't specify a number of rows by just leaving this blank or not passing num rows, then I'm going to get all the rest of them. And then at the end, I'm going to return a matrix because I want my read matrix function to read the file as a matrix. So I pass in the length of the data, which will be the number of rows, and then total columns. I know from up here, right? When I first opened this file, I read those in, so I'm going to trust that value. So I know the number of rows that I just read and the number of columns, and then the data itself gets passed as a third argument. So this is just the ordinary matrix constructor that's going to give me a matrix back in my code. It also turns out that in a lot of cases, as I started to use this, I discovered that I was calling the close function on this matrix reader. I was calling this guy a lot right after I did a read matrix. So I thought, well, let's stick in a parameter here that lets me call that if I want to. So close is just going to be a Boolean value, and if you pass close equals true, it will read the matrix and then close the file, so you're cleaning up after yourself. And if not, it'll just leave the file open. Matrix writer, I'm not going to go through this in detail. It's really the opposite case of the matrix reader. Very similar structure. It opens the file pointer, except now because we're writing a file, the next thing I do is store the number of rows and columns out to the file. This is also broken, that should be FP. There's a close function that shuts it down when we're done. There's a write rows that iterates over the rows and does the opposite operation using a list comprehension to construct a string containing all the values of the initial integers in the row and stores that out to the file with a file equals option. And then a similar thing for writing the matrix, which basically just it gets a matrix, just like the other one returns a matrix instead of a list of rows. And in order to write the matrix to the file, we actually have to reach inside that matrix and get its data attribute, which is where the array of arrays is stored, and that writes the resulting file out to disk. So very similar to the matrix reader. You can see that that's actually a fairly common pattern to have, the object that you're manipulating, the matrix in this case, and then have some kind of adjunct classes that know how to do I/O with that thing. And I feel like this is still a little bit complex in terms of dealing with the row and column counts and having to be able to load a subset of the file in at any given time in order to distribute it out to the parallel processes. But this, I feel like, cleaned it up a lot compared to when I was trying to jam all that stuff together into the matrix class itself. Okay, so let's go back and take a look at another sort of support file here. Actually, let's look at the addition code now that we've talked about those things in detail. So here's a serial a version of matrix addition. You can see here that I'm bringing in, let me make this a little bigger. I'm bringing in from the matrix file, I'm bringing in the matrix class as well as the reader and the writer, which makes sense because we're going to read some matrices off of disk. We're going to add them together. We're going to write them back to disk. this is how you do sort of the equivalent of get-opt from C, but in Python. It's actually quite a lot more elegant and more sophisticated. There's a standard module called argparse, and you create your own argument parser. And then once you've created that parser, you can add arguments, and those can either be flags with dashes, or they can be positional arguments, which is what I've got here. So I've got 3 arguments called A, B, and C, and those are going to basically be the names of the files that contain the matrices that I'm going to add, and the name of the matrix that's going to contain the sum. And then you call parser.parseArgs, which actually goes ahead and parses the command line arguments, and it sets up this args variable with the details of what showed up on the command line. So what we'll see here is, and I'll come back to this timer thing in a second, but so here I'm invoking my matrix reader. Now the way you access these, the values that were passed on the command line after calling the parse args, is to use that args object, and you can just say args.a, and that a corresponds to this a, right? So if I called it Fred, I could say args.fred. So it basically just says, use the name that the user supplied as the first argument on the command line that we've called A as the name of the file. So that tells the matrix reader, basically call the constructor, open the file, read in the number of rows and columns, and hand back a matrix reader object. Well, I don't really need to hang on to that matrix reader object as a standalone thing. I want to just go ahead and read the matrix. In this case, when I'm doing the sequential algorithm, I'm not trying to read it a piece at a time to send it out to the other processes. I just want to read the whole thing in. So I call that read matrix function that we just looked at, that's defined as an instance method on a matrix reader. And additionally, I'm going to say close equals true, so that when the thing is done being read, the matrix reader will close the underlying file. And notice that I'm not giving it a number of rows here, because I just want it to read the whole thing in. So what comes back from this, again, I feel like this is a pretty nice API, which suggests that maybe this is a good way to go in terms of architecting those underlying classes. But what's going to come back from this read matrix, as we saw previously, is an instance of the matrix class. So I'll just assign that to A. And then I'm doing exactly the same thing here with the B matrix, except I'm going to read now from args.b, which will be the second argument we supplied on the command line. And then same thing, read matrix, close the file when you're done, and give me back the matrix and store it in B. And then I'm going to do the addition, right? Because A is an instance of a matrix class, and B is an instance of the matrix class, and I define the Dunderbar add function in there. That's going to call that function passing this as self and this as other. And the result is going to be a matrix, which I'm going to capture as the C variable here. And then finally, I want to write C back out to disk. So I'm going to call matrix writer instead of matrix reader, obviously. And matrix writer takes the size, the rows and the columns, and then the actual matrix. So I know, because the add function makes a bona fide matrix instance that I've stored here at C, that it's got a rows and a columns attribute. So I can pull those out of the value of C. They're going to, turns out in this case, they're going to be the same as the values of rows and columns from A and B, but that's immaterial. And then I'm going to use args C, which will give the third positional parameter from the command line, and that will contain the name of the file I want to write the matrix to. And then I can call that write matrix function that takes a matrix. It also took a row count, which I've omitted here, so it's going to just write all the rows. And then at the end of the process, it's going to close the file by having passed in that close equals true function. And we're done. Now let me go run that for you, and then we'll come back and talk about this timer thing. Shell. So, actually I have got some changes that I made here. I have a make target that does this called test sequential. This will run for us. Ooh, and that cratered. Okay, so the command that's actually being issued is right here, Python 3. I could just say Python in this case, because both are linked to the same thing in my virtual environment. I'm calling matrixadd.py, and I'm passing in 3 values, a.data, b.data, and c.data. So these are file names that will be interpreted internally as that args.a, args.b, and args.c. Not because I've called these a, b, and c, but because that's what I named those positional parameters inside the addition function. But I don't have any data files yet, so I've got another target. Let me just show you the make file here a second. I find it super convenient to just use a make file to do kind of common operations that I might want to do during testing and stuff. So you can see here's that test sequential make target that runs the matrix add function with Python. It's pretty common in a make file to include the names of executables as essentially like a constant declaration. So I'm saying up here Python equals Python 3. If I wanted to point it to a different Python, I could do that in one place, and everybody that used Python would do the same thing. I've also created a thing called timed Python, which inserts the time keyword that tells the shell, hey, figure out how long it takes to run this command, which is something I use when I'm generating larger data sets. So this will just run Python 3 and then those values. But right now I don't have any data files. I didn't include those in the tarball, so you don't have those yet. But I provided some what seemed like reasonable values here for creating data files. So I'm going to just do this tiny data one. It's going to run Python on genmat, which generates a matrix, a certain number of rows, a certain number of columns, and the name of a file. So if I go back to the shell, I'm going to just do make tiny data, and that's going to completely crater. Now I could have gone back in, I guess, and edited that out, but I wanted to show you that I actually screwed something up here which caused that error. Remember when I was showing you the matrix.py code, I was telling you about in these the reader and the writer that this should be self.fp.close. Because I was thinking, well, what I'm trying to do here in the destructor of this class is shut the file pointer down so that I'm not using that resource. In fact, the way that I wrote this initially was to actually have the destructor just go ahead and call the close function, which knows to check to see if I've already closed that file pointer because it's got a none value, and then do the actual close. So I introduced an error by adding that to the destructor, which I shouldn't have done. So just full disclosure here. So having returned the code to its pristine glory from previously, if I go back here and do that make tiny data, now we'll see that it actually executes properly. So Python 3 again calls genmat with a number of rows and columns and constructs that data. Now if I do my test sequential, it should run that matrix add function and give us some output. So now if we look at our data files, you can see there's a.data and b.data. Let me just show you one at a time actually. So there's a.data. You can see the first line tells us it's got 12 rows and each row has 6 columns, and then the data follow. And b.data is a similar format with different random values. And because we just ran the add function, we also now have a c.data that contains the sum of those two input matrices. Okay, so what about this? Let me run that again so we have a current version of it. What about this crazy output here? What I wanted to do was kind of give you a little tool to help you measure different parts of your algorithm as it's executing in parallel. So I've created this thing that I've called multi-timer or something like that. And what it does basically is it gives you a real-time, fairly high precision clock that tells you how long things are taking. So the output here, when it starts, it creates its own kind of log entry that says when it started, and when it's completed, it creates its own kind of little stop entry. And the output, and then the intermediate ones are things that you can say, okay, I want to have the time at this moment, and I want you to give it a label of this string. So I've created a read, an add, a write, and a complete label. And what's coming out here is the value of the timer. So this is a standard Python timing thing that just kind of tells you the relative time at which these things started. And then I've post-processed this to come up with the deltas, right? So the difference from start to read is this value, and that would be in seconds. So it's some small number of microseconds, and then the rest of these deltas show up in in similar fashion. So this is the amount of time that the read took, the add took, the write took, and so forth. And then I've also split out a percentage of the overall runtime for you. So the tall poles in the tent are the read, which took almost 60% of the time, and the write, which took 35% of the time, and the add was relatively quick, only 5.25% of the time. And then this last value here that's bracketed is the total time. There wasn't another delta to put in here, so I just thought it'd be handy to have the total time. So in the source code for the matrix add function, you can see this multi-timer function or multi-timer class I'm bringing in. I instantiate an instance of that at the beginning, and then to tell the timer to sort of grab the current time, you call record, and you give it a string that says what you want to use for the label that shows up in the output. So this says, I'm basically saying I want to know when I started to do the reads. I wanted to know when I started to do the add, when I started to do the write, and when I'm done. And actually, this is kind of redundant because the MT package does that for us. So I'll see if I'll shoot myself in the foot again here. Let me run this one more time. And yeah, no, I just got rid of that complete, which was kind of unnecessary. Okay, so what we'll see is that in a parallel formulation of this, we can also use this multi-timer to kind of figure out how long things took at various stages in the parallel algorithm. Just quickly, the multi-timer source is pretty straightforward. It keeps track of the labels, the time at which you called the report function. There's this flags thing. Here's the invocation of the record function at the time of construction. So that if I go back to the shell here, you can see that start entry shows up there. That's just put in there automatically. And then when you want to add a new thing to the timer log, you call record and you give it a label like read or add or write. And then this perf counter, which you can see here is coming from the standard Python time module, that's supposed to give you a good timing for performance monitoring, which is why it's called that. So that's a standard Python part, which is really handy. So I grab the current time right as soon as I can because I want to get as accurate a measurement as I can when I call that record. And then I'm going to add to this list of labels the current or the label that was passed in. I'm going to add the current time, and I'm also going to add something from this flags value. I'll come back and talk about that in a second. So that's just supposed to be a really quick way to grab the current time that record was called. And then, as you can see in the source code, at the end here, I call the other method defined on this class called report. And it is going to, first of all, it adds a stop record so that you can see the time that everything came to a conclusion. So I'm assuming that you call this at the end of your function, which is kind of on you. And then this just is associated with kind of formatting this output so it looks nice and is readable and stuff. Let me also show you what this flags thing does. If I go back here to my matrix add function, I thought it'd be handy to be able to sort of distinguish a particular piece of output here. So if you say flags and then give it a number, I'll say 2, and then I'm going to run this again, what you'll see is that I remember that I flagged the add record, and what you see in the output here is the add record now has 2 little stars next to it. So this isn't so useful here with a single process, but when you start running multiple processes, it's a little bewildering because you're going to get this kind of output from every process. And in order to kind of quickly go through and visually and find the data that you're looking for, I thought it'd be handy to be able to stick a little flag at the end there. And if you wanted to do more than one of those, you can. And if you want to have like one really long one and a couple little short ones, you can give a different number to that flag's optional argument. Okay. Talked about the matrix, talked about the timer. Oh, let's look at the matrix generator. This is a kind of a nice simple way of using those underlying matrix operations. So we did this when we in our shell when we did the make tiny data. We called matgen, and we passed in command line arguments that say how many rows, how many columns, and what file to write to. again, I'm using that arg-parse argument parser, a little bit more sophisticated version here because now we're putting in command line flags, which are optional, although I guess I've made some of them required, or they can be optional. So you have to supply either --rows or -r and an integer, and that's a required flag. And same thing for columns. If you want to change the range of values that are being used to generate the random arrays, you can also pass -min or -max with an integer to set the upper or lower bound. And then there's one required argument, which is the file name. So that's a positional parameter that has to be there, or the arg parser will freak out on you. And we store those things again with in args. One of the things I'm checking here is that if the minimum and maximum values don't make any sense, and specifically if the minimum is greater than the maximum, I'm going to raise a runtime error. So args.min is going to be the value that was pulled from this parameter, and max would be pulled from that parameter. And those are optional, so those also have a default between 1 and 100. Once that's all set up, we're going to call a matrix constructor, and we're going to use the random one and pass in the number of rows, the number of columns, the min and the max value. And it just turns out that with this little generator program, the min and the max also match the defaults, but they wouldn't have to because these are kind of independent things. So I decided to pass them anyway. And then I'm going to call the writer. So call the matrix writer and pass in the number of rows, the number of columns, and the name of the file you want to write to. And then here I've got an invocation of write matrix of that matrix and close the resulting file when you're done. I guess I could have combined this like that as well. Okay, so that's what's being run when we are when we're creating the matrices. So again, I've got a bunch of make targets that allow me to do different size things. Tiny here, I use 12 as the row count because it's divisible by a bunch of different things, right? So you wanted to create a little larger array, make it, the reason that there's 360 degrees in a circle, right, is really handy because you can divide it a bunch of different ways. So if you're trying to come up with a convenient data set size and you want to be able to split it in half or in thirds or quarters or sixths or whatever, tenths, you might choose to use a multiple of 3 like that. And then I've got some other sizes here that are larger for testing different kind of performance levels. And then again, here's my test sequential, and you can see here there's also an MPI version of this that's available, as well as some code to make the handout and clean things up. Okay, so I'm going to just stick with the tiny data for the time being, because that's sort of sufficient to illustrate these ideas. Now, so what about MPI? Let's look at hello mpi.py. I think that's the last file in here. Again, you'll want to make use of some of those resources that I mentioned at the beginning to get more details on the different things that are used in these Python MPI programs. But this illustrates a lot of them, a lot of the ones that you're going to need for sort of straightforward implementation. So first of all, you've got to load the MPI class in from the Py for MPI module. So all these things kind of start out with an MPI something or other. And I'm also using that multi-timer in here to show the behavior of the algorithm as we go. As we did in the C program, we're going to use a particular communicator. In the C version, you used MPI_com_world, and that just was an identifier that was passed into the various communication functions. It's a little different in here in that the MPI is more of a namespace than just an arbitrary prefix. So we've got to say MPI.com world to get that global communicator object. And then once we have that, we can call getRank and getSize to come up with our current rank and the total number of processes that are executing. And then here I've declared the timer, which will also create that first start record in the timing. Now, in the samples that we looked at in class, I was kind of just using a conditional, right? If my rank is this, then do this. If my rank is not that, then do something different. That works okay for relatively small programs, but you may have discovered already in the matrix addition program that you did in C that gets a little dodgy, right? You got to declare some things that have a wider scope than you really want to, because you've got to have several blocks where you have the if rank equals 0 or something like that. So another way to structure your code that I think is preferable is to define functions that are going to run on certain processors. So you can see here I've defined a function called even and a function called odd, and those are going to be the main functions that are going to be run, in this case, on processors that have even ranks and processors that have odd ranks. And this little example here is just basically the same idea as some of the round robin thing that we talked about in the early going here in the MPI topic. Let me just run this for you so you can see what it does. Shell, thank you. So I want to run that hello MPI program, so I'm going to do MPI exec and say number of processors equals just 2 to start, and then I'm going to call Python 3 on MPI, or sorry, hello. I should create a make declaration for this, which I don't think I did. So that's going to run that hello MPI program that we were just looking at. And here's what happens. You can see here that now we have 2 sets of output from the multi-timer. So start and a stop, and all that these do is the even number processors, including 0, are going to send some data from one process to another. So it's going to send this structure to process 1, and here's the absolute timing as well as the deltas and the percentages. And then on process 1, the odd processors are just going to read from the even one that's one number lower than it. So this isn't even as elaborate as the round robin thing we looked at earlier, but that's the output. So back to the code, you can see here that the even number processors that are going to be invoked with this function, they create a Python dictionary, right? That's got their rank in it, as well as a random number that we're generating on the fly here. And then I'm calling my multi-timer to just record the fact that I'm about to send something. And then I do the send. Now you can see here that this send is a lot simpler than what we are used to from the C version. So we're using that communicator again, and it's the class in which the send function is defined, which makes sense, right? Because the communicator is supposed to encapsulate the ability to send information back and forth in the multi-computer. So we call send. That's going to be the blocking send. There's also an I send and a broadcast and everything else. And it's a lot simpler to call this guy. We just basically pass the data we want to send and the destination rank where we want it to go to. So the even numbers send to the next highest odd numbered processor. And then on the receiving side, the odd numbered processor is going to receive from the next smallest even number. So all it's got to do is call the blocking receive in this case and set the source parameter to rank -1. And then it prints a record of its accomplishment after it receives that value. Some things to note here. This, again, is just an ordinary Python data structure. And the neat thing about the MPI for Pi library is that it knows how to send those things around and sort of serialize them, send them across the wire, and then deserialize them on the other side, expand it back into the normal Python class, or in this case, a dictionary. So the data that comes back from this thing is going to be a complete duplicate of the data that I sent from the other process into this process, and you can see that really clearly in the output based on what's being shown here by the multi-timer. So I go back to the shell, you can see that's where this came from. Process 0, the even numbered processor, is sending that structure to process 1, and when process 1 gets that in, it shows us what it got, and it exactly matches the thing that was sent from process 0. So no messy size, types, all that kind of stuff. It's all dealt with for you under the hood by Pi for MPI. MPI for Pi. Okay, let's just for completeness here, let's bump this up to 4 and see that it works, similarly. So the even and odd processors are changing hands. So once you've defined those functions that are going to be called for specific processors, that you just basically need to orchestrate the invocation of those functions appropriately. So in this case, I'm always going to call the even function if I'm on a rank that has an even value, and I'm going to call the odd function if I'm on a rank that has an odd value. So it couldn't be simpler to kind of kick things off. And although this kind of reduces some of that tendency to sort of declare things in wider scopes than you have to, you also need to be able to kind of keep your head around the notion that although these are going to be sort of a self-contained function called on a certain processor rank, that it's going to interact with the other processors as well, right? So as you're writing the code inside of, in this case, even and odd, you've got to make sure that that the tracks still line up. I feel like on balance, this approach is cleaner. It helps you sort of keep the scope as local as you can for different variables and stuff, which is good. But it's not without its challenges, because you still have to make sure that you orchestrate the interaction of the two processes. The last thing here in the main function, I got a little error checking here to make sure that I call this with the appropriate number of processors. It doesn't work if I have an odd number of them. So I verify that up front and then just crater if it's not being called correctly. At the end here, I'm using the barrier function in order to kind of sequence the output of that timing data. If you think about it, when we call that, if I go back to my multi-timer source code, this report function actually outputs a lot of stuff, right? It's constructing the lines and filling them in and doing other weird things. And if I were to just have all of the processes start sending output to the standard output, it's just going to end up being a complete mess. So what I'm doing here is I'm sort of forcing the processors to act sequentially. And that's something you never really want to do, in the business end of the algorithm. But when you're just reporting the results after you're done timing things and all that, it's totally fine to sort of enforce kind of a sequential behavior. And there's different ways to do that. You could pass a token around the processors in order or something like that. But this is another approach to that. So I'm using barrier, and remember that a barrier is a function that everybody has to call before anybody is going to be able to continue in the next statement after the barrier. So what I'm doing here is I'm going to loop over the number of processes, and everybody's going to call the barrier. After everybody, which the first time through, anything that happened earlier than this loop, everybody's going to have to finish all that calculation. And obviously in this case, I've finished the interesting part of the calculation. And then they call a barrier. When they're all there, then the first process, then they're going to leave the barrier, and then the process number I is going to report its values. And then everybody's going to loop back around to the barrier again. So everybody except processor I, the one processor that's going to be reporting at this moment, is going to enter the barrier, leave the barrier, and then just loop back around and hit the barrier again. And each time through that process, you're only going to have one processor at a time that's going to be enabled to call the report function to generate its output. So it ends up making the output nice and orderly, as we've seen here. One other thing here about the MT report, this thing takes a parameter, an optional parameter, and in this case I'm passing the rank formatted as a string with two characters wide and a space. And if I go back to the multi-timer, you can see here there's an optional parameter here called prefix, and if that prefix is present, it basically just adds that prefix to the beginning of each line in the output. And that's what's generating in our shell. That's what's creating this 0, 1, 2, and 3. You could prefix that with anything, but I just thought that that was a simple way of showing the processor that was giving you that output. And this is not required. Python obviously doesn't require a main function like C does, or Java. But I find that it's sometimes helpful to create a main function just to kind of organize the code a little bit more clearly. And then, of course, you got to remember to call it at the end. One final thing here that you might be interested in is this test function, test file. This uses a standard, not a standard library, but a really popular third-party library called PyTest to run a bunch of tests on the matrix classes itself. I wrote this kind of early on, and I didn't really come back in and try to enhance it. But it tests a variety of the functions that are in that matrix class, and it'll tell you if something goes haywire. We kind of haven't been emphasizing testing a lot in this course, but obviously that's an important element of writing robust software. And it's super easy to actually run these tests. The fact that that the file is called testsomething.py means that the PyTest program will actually find those files and execute all the tests that it finds within. So if I run PyTest, you can see here that it found that testmatrix.py program, and it runs all the tests in there and says that six tests passed in 0.02 seconds. So I got 100% success rate in this particular output. That's a really handy function or handy thing to have around to do your testing, and I'd recommend that you check out the documentation for PyTest and learn how to use that for your Python code.